Okay, now I'm going to tell you another interesting aspect. This simple device, maybe, without mentioning, you don't realize what type of system it is. But let me just ask you. Well, now that we know B, right, we know the solution for B, the flux density, is equal in the gap and in the core. What does it take to calculate the flux? The flux is the flux density multiplied by S, which means the flux is telling you, well, how much field lines do I have in this area, right? Okay, so I multiply by S to B. If I somehow change the math, so I have in the numerator mu 0 and mu together. If I divide mu 0 and mu on the top and bottom, what do I have? And I move this S to the bottom. So now I have rewrote the flux. Now this is a real test to you. I know you passed your second examination, so you forget everything, but I'm hoping you're not forgetting everything. Whenever you look at length divided by area, and then also divided by some weird constant, what do you think of? What's the first terminology that you think of? Oh, this is sad. L divided by sigma and S. What is that called? Resistance, right? If for a conductor, we know its conductance, we know its length, we know its surface area, this is called the resistance for that conductor. Now, you look at this mathematical formulation. I have the length of the core divided by its surface area and also divided by its mu, permeability, right? Plus L gap, its own permeability, its area. Can you somehow guess which direction am I leading you to? I'm actually trying to sell the message. This is some kind of circuitry. Believe me? No? Don't believe me. I never lie, really. I like to make jokes, but I never lie. Think of an electric circuit. An electric circuit, if you have two resistors making serial connection, 串联, then this circuitry is driven by some voltage source, right? You provide voltage, and you have two resistors in series, then you know how to calculate the resulting current, right? V divided by R, I is RF plus RG, right? So now take a good look and try to compare to the mathematical equation we have now. Now the fact is we have some magnetic core material connected in series with the air gap. Is it possible that we formulate this geometry into circuitry? We actually have the core material connected in series with the air gap. Each has its own permeability, each having its own length. Okay? So now take a good look. The physical meaning of magnetic flux is now very apparent. Inside an electric circuit, if you have two components connected in series, what is the same? What parameter, what quantity is the same thing shared by the two resistors? They have the same number of electrons flowing across them per second, right? The current. Now we move into the magnetic circuitry. We have the magnetic core connected in series with an air gap. What is crossing or flowing across these two regions? And they share the same value. Our initial assumption is we don't have magnetic leakage. So all the magnetic field lines remain the same, right? So for a magnetic circuitry, what is being flowing across? The quantity that is shared is phi, the number of field lines. They actually share the same number of magnetic field lines. Magnetic field lines are used to connect between these two materials. In comparison to electric circuitry, current is the quantity that they share. Okay? So, it should be very apparent why we name this N times I0 as the magnetic motive force. It's like a current source, right? If you want to drive an electric circuit, you want to have maybe voltage source so you can produce current. For magnetic circuitry, you want to have some maybe current source to drive the circuitry, right? So in this case, this Vm equals the total number of current you have is called the magnetomotive force. Just like voltage. The function is just like voltage. But the way they link between these two magnetic components is through sharing the same number of magnetic field lines. So that is quantified by the magnetic flux. So all these, L divided by mu s, are called reluctances, 磁阻. Do you happen to know the meaning of reluctance? Reluctance? Reluctant. Reluctant. At T. Anyone knowing that word? Reluctant? 心不甘情不愿. Yeah. Okay. So are you reluctant to take this idea? Or are you very willingly to take it? Please do take it without reluctance. Okay? I hope we don't have reluctance between you and me. So today, I actually covered a lot of concepts. Okay? This might be brand new to you, but starting from now, you should realize whatever we have in the world of electrics, we can find a counterpart in magnetism. So in terms of circuitry, in terms of resistance, we have reluctance. In terms of voltage source, we have current source. In terms of current, we have flux. So tell me, take a good look at this simple equation. Summation on the left equals to the summation on the right. What is it called? Well, if you change this, right, Ni is voltage. It's voltage. Reluctance times phi, you convert it to resistance times I. What equation is it called? Should be called? In the world of electrics, I hear some answer from the back. Yeah? KVL, right. So it's sad that we're born so late and we cannot coin the equation under our name, but this is the magnetic counterpart of KVL, Kirchhoff's voltage law, right? You see a one-to-one correspondence. It's very interesting. But in the past, I think this is something you never learned in high school, right? All the previous things you might have touched in the high school, but I mean, this one is maybe new to you, okay? All right, so the following 10 minutes, very simple, like a general education course, 通识, okay? The classification of magnetic materials is basically looking at what type of mu r that material is giving you, okay? Simply put, we can classify materials into 3 types: diamag, paramag, and ferromag, right? They are all depending on the mu r they produce. For diamagnetic materials, okay, when you apply external field, diamags can give rise to induced magnetic dipoles, but in a reverse direction. So what does that mean? Here you apply an upward external field, but the dipole moments generated inside this material would give you a current so that all the dipoles produce a counteracting field line. Okay? So in this case, you have a diamag suspended in air. So can you think of why? This is like me floating in air and teaching you this course. I mean, don't laugh. It is possible. Really, it is possible. Let me show you this picture. This is a movie. It's a live frog. It is still live inside very strong magnetic field. So the frog is floating. It's moving, but it's floating. It's suspended in air. So maybe one day I can just float in air and just offer the course. It will be very fancy, right? So it is true. So in this case, you do have the ability to generate induced magnetic dipole moments, but in a reversed direction. Therefore, your mu is smaller, it's negative. Basically, it's just negative, right? Chi is negative, so mu is also negative. So be aware, when I talked about this relationship, I used the wording. We have the chance, we have the potential to create more magnetic field lines inside a magnetic material. I use the wording potential and chance. Due to this fact, if you choose the wrong material, you choose diamags, you're doomed. Diamags are pretty much the dielectrics, right? Dielectric materials produce counteracting dipoles, dipole field lines, right? So if you choose the wrong material for that ring, you still get fired, okay? Please do choose the right material. You need to have mu value, which is positive and huge. So in this case, mu is small but negative. Well, you can make a fancy movie and attract the students. Students that are falling asleep, show this movie. Okay, that's the only purpose for diamags. It's functionality to attract students. Paramags, in contrast, they are giving you positive chi-m. It's indeed positive, but very weak. How weak? 10 to the minus 5. So it's basically not there. Okay? So paramags, 顺磁, okay, they generate induced magnetic dipole moments pretty much in the direction of your externally applied field, but they're very weak. So overall, as a sum, it's there, but you don't really feel it. 10 to the minus 5 is really not big. Okay? Then we come to the material that we encounter on a daily basis, like permanent magnets. And there's called ferromagnetic materials, 铁磁. Okay? Basically, you have cobalt, gu, nickel, nie, 铁, iron. Okay? So these three are the common substances that can provide you ferromagnetic responses. So for ferromags, you have very strong chi, meaning your mu is very big. Okay? So in our ring, usually we want to have ferromags. Okay? I'm not going to go to the details, but this is something you know already, hysteresis, 磁质效应. Okay? If you have a ferromagnetic material, when your externally applied field is weak, your B is increasing, right? As you increase your externally applied field, your B is also increasing, meaning that you're getting more and more magnetic field lines. But in a nonlinear way. Looking at this trace, this is not linear. So it means for ferromags, B is only proportional to H, but maybe in a nonlinear way. Maybe to the second order, third order. It's nonlinear. Okay? So when your externally applied field is weak, you start to increase it to a certain point, and then you decrease it, right? You come back. So without externally applied field, this material remains to be non-magnetized. But ferromags have this particular special unique feature is when you apply a huge enough external field, and once you turn it off, your ongoing path and your off-going path are actually different. So somehow, even though now without any applied field, your material remains to be magnetized. So at this point, you have fabricated a permanent magnet, right? The thing we use every day. So let's come back. Why did I spend so much time in talking about this example? This is the perfect device to fabricate permanent magnets, right? You place your ferromagnetic material into the gap, you turn up your current, and then you turn off your current, and then you have a permanent magnet. And the benefit of this structure is you don't really need a huge current, right? Because you're using the core to produce lots and lots of field lines, right? So this example, the usage is directly linked to fabricating permanent magnetics using ferromagnetic materials, right? You want to achieve a high field value so that when you turn it off due to hysteresis, the entire material is still magnetized, meaning it has its own north pole and south pole. Okay? Questions up to now? If not, please do preview the course lectures before coming into class on Wednesday, because on Wednesday, the very last slide is very unique. You cannot find it anywhere in any textbook. It's purely my copyright, okay? So please preview the last page before coming in, and we are going to discuss the special features of only allowed by magnetic fields. Okay?